it's a great, great pleasure to bring Professor Fogler to talk to us. Professor Fogler doesn't need any presentation. His name is strong enough. Everybody knows. Everybody got so excited when we announced that you were going to talk to us this morning. And it's a pity that you cannot be here, but now virtually you are. And I hope people enjoy a lot and you have fun talking to us this morning. Professor Fogler, the word is with you. Thanks a lot for your promptly answer to this call.
You're welcome. Thank you, Veronica. And it's always fun to talk to the students in Brazil. I think Enrique is on this call. Excuse me. It was about a year ago, Enrique, I think a little more, that I visited Sorocaba, and you showed me around and had a nice time visiting with the students and everything. And I hope to do it again sometime in the not too distant future. So my seminar today and what I've been presenting is on safety across the chemical engineering curriculum. And wait a second. Okay, there we go. And if I can get this out. Wait, is there a way to get? Okay. Oh, right. I don't want to see the waiting room. Anyway, a critical aspect of safety. Veronica, when you see the people in the waiting room, you'll just go ahead and admit those, right?
Yes, don't worry about it.
Okay. It's sort of blocking my screen is the problem. So anyway, chemical process safety is a blend of engineering and management practice focused on preventing accidents, particularly fires, explosions, toxic releases, which result in the loss of life and property. Professor Trevor Kletz, who you can click on and learn his biography, is really considered the father of chemical process safety. What surprises most people is that almost all these chemical engineering accidents were preventable. Most disasters are the result of poor engineering decisions made by just a handful of people who lacked a fundamental understanding of the consequences of their actions and basic chemical engineering concepts and chemical engineering safety. The best way to prevent future industrial disaster is to understand how to effectively and safely design, operate, and troubleshoot chemical processes. Sometimes safety is taught in a separate course in the department, like you have heat transfer and so on. And sometimes it is only taught the senior year as part of the process design course. So here's the course that's taught at Michigan. It talks about, it's once a week for 2.5 hours, and it usually has people from outside the university, from industry, come in and talk. It's led by Ken First. So this is the course we offer. It's offered Thursday afternoons at 4 o'clock, and that's not a really good time. So how many people do you think attend this course? Anybody shout out? How many people come to this course to learn about process safety? Anybody?
No one.
No, a little more than that. Well, okay, we have about 100 students graduating every year. And at best, 9 to 14 take that course. So that's not very many. So the purpose of this website is to provide case studies and resources so that process design, process safety can effectively and easily learn throughout the chemical engineering curriculum. So if somebody just took that course, we're only going to reach 10 to 14 people out of 100 that are graduating. But if we offer it throughout the curriculum, then we'll reach much more. So here's our curriculum at the University of Michigan. We start with energies, then we come over to thermodynamics and fluid mechanics in the second year, and then third year is heat and mass separations, chemical reactions in laboratory, and then process dynamics and control. So here are our courses throughout. So what this website does is provides a module in every single core course in chemical engineering. So how some, there we go. Okay, there we go. Okay, so at the University of Michigan, as I said, we have 120 seniors. 10 to 4 take this 2-credit course. Now, other courses in the United States have a safety assignment, maybe in the senior design course, or to get the SASH certificate. So that's still, we're only reaching about a small percentage of our graduating seniors that have a mindset about chemical process safety. So this, what we do here is to try to get every person leaving that thinks about process safety when they go out onto the job. So we've developed this website. So let's look at this website briefly. First of all, we're going to talk about the components of a safety module. And then here's all the courses that are covered. So you just click on one of those courses you want. Now there's tutorials, the NFPA diagram and the GHS diagram, the Swiss cheese model, the bow tie diagram, process safety, fire triangle, safety analysis of an critical thinking applied to safety algorithms. Then we have other resources, the CPS safety beacons, and I'll end up in the spotlight. And now down here on this side, we have the complete safety module with solutions. Now, if you click on here, the professors can go in and see the solutions to these modules. And all you have to do is email me, the professors, not the students, but the professors, and I'll tell you how to access the solutions. So this is the website that you can go to. You can come up here. I'd like you to learn a little bit about Trevor Klutz. He's from the UK, and he, again, is the father of chemical process safety. So we have a module in every single course in chemical engineering. What does a module consist of? The first thing you do is view the video. After you view the video, you fill out a safety analysis. Then you fill out the NFPA diamond. What's the fire hazard? What's the health hazard? Then you do a bow tie diagram. Now, basically, the bow tie diagram is going to be quite easy once you fill out the safety analysis. And then you do a calculation specific to the course. So these are the 5 components of the safety module. And I think the best way to do this is to go through one specifically. So first, let's look at the tutorials. One is the NFPA diamond. This can be found putting on containers. What's more used now is the global harmonized system. This is particularly used in Europe. So one of these stickers would go on explosive, oxidizing, harmful irritant, and so on. So rather, this will be replaced the NFPA die. Also, the Swiss trees model. And this is, you're going to have put up barriers, but there's always going to be a way through these barriers. You're going to have an incident. You're going to put controls, but something could, you have to plan on something getting through. So here's what we want to get ingrained in every student. This is a safety analysis of the incident. So the first thing you do is to view the video. Then you come and say, what is the activity? What is the hazard? What is the initiating event? What could have prevented the accident? Okay, I couldn't prevent it, but what can I do to mitigate the accident? And then what did I learn? So, and these are all spelled out. The process, hazard, incident, initiating event, what could have prevented it, and what could have mitigated it. Then you go and you want to construct a bow tie diagram. Here's what it looks like. Here's where you have to be creative. You try to think of all the potential problems that could go wrong. For each problem that could go wrong, you come up with a preventative action. And so you have a potential problem for preventive action. Then you have a hazard up here. Now you have to have something that initiates the event. So you tried to do all that prevention, you couldn't do it. So now you have to say how you would mitigate the actions, and then what are the consequences. Okay. The process safety triangle is just a reminder how sloppy you're getting at work. You start recording all the unsafe acts that happen during the course of a day, year, month, or whatever, and what they are. And then you're going to have the near misses from these unsafe acts. You could have a minor injury, lost time, serious injury, and a fatality. So if you have a lot of unsafe accidents, they're eventually going to lead this way. Now in the U.S., some companies like BASF they record every unsafe incident and then say, what they could do from not having that unsafe incident happen again. So let's go through one specific module. I'm going to come down here, and we're going to look at thermodynamics. So I'm going to come over here, click over here. Then I'm going to come up thermodynamics safety modules. We're going to look at the Prox-Air cylinder fire and explosion. So here we are at the fire and explosion. What it is, problem statement. It was a hot day and direct sunlight was coming down on the cylinders stored outside. So now we come down, we click on the video.
On a scorching day in June 2005, propylene gas, venting from a cylinder at a compressed gas filling and distribution facility, ignited, setting off fires and explosions that lasted 5 hours. On June 24, 2005, St. Louis was experiencing a heat wave. The high temperature that day was recorded at 97 degrees. At Prox-Air, thousands of compressed gas cylinders containing highly flammable products such as propylene, propane, and acetylene were stored outside in the direct sunlight. As the sunlight beat down on the cylinders, heat also radiated from the asphalt, driving up the temperature and pressure of the gases inside the cylinders. At about 3:20 p.m., increasing pressure inside one cylinder activated its pressure relief valve. Gas pushed against the spring-loaded plug, allowing propylene to flow around it. Gas moved past the spring, out of the valve, and through openings in the cylinder cap. The propylene vented to the outside air and formed a flammable vapor cloud around the top of the cylinder. A static charge, created by the venting propylene, most likely ignited the vapor. A Prox-Air security camera recorded the vapor release and ignition. The vapor begins escaping from the cylinder seconds before 3:20 p.m. It ignites immediately. An employee sees the fire and sounds the alarm. Within 30 seconds, the fire is spreading rapidly, heating surrounding cylinders, causing them to vent gas, adding more fuel to the flames. Just over 1 minute after the initial vapor release, smoke begins to darken the facility as the fire rapidly grows out of control. 90 seconds into the incident, the camera records blinding flashes as cylinders begin to explode. Cylinders begin rocketing through the air, further spreading the fire.
Okay, so they've seen the video. So now what they're asked to do is come and do a safety analysis of the incident. What was the activity? The activity is storage of propylene cylinders. Hazard, flammable propylene. Incident, the pressure in the storage tanks reaching the set point, which vented propylene. The release of the flammable gas led to the explosion. So we start filling out this activity, hazard, incident. What was the initiating event? The release of propylene due to increase in pressure. Preventive safeguards. Well, what could they have done? Maybe they could have stored the cylinders farther apart or put barriers between them so that if one cylinder caught fire, it wouldn't get the other. Mitigating actions. Well, they could have had maybe a sprinkler system. They could have covered preventative action. In terms of preventative action, they could have put sheds over the cylinders to direct them from the sunlight. So those are preventive actions. contingency actions could have been a sprinkler system that would come down and cure that. So that's what they do for this incident. Now we look at the safety module solutions. They had to fill out a bow tie diagram as well. So, okay, potential problem would be a mechanical failure of the valves. What would be preventive action? Routine inspection, routine replacement. Here's the hazard. The initiating events was a gas leak. What would have mitigated? A gas detection system, lightning rods or resistors, reduced static charge. So these are the things that could prevent it, and these are the things that could mitigate. And it's important we understand prevent, it happened, now mitigate. And so the students then are expected to fill out this bow tie diagram. The next thing they do is they do a calculation specific to this module. Now, if they're asked to, in this case, what is the pressure inside the cylinder? And they're asked to do a calculation using the ideal gas. And if they do that, they'll find that the pressure is way below the set point of the cylinder. But in the cylinder, we have two phases, liquid and gas. So therefore, we cannot use the ideal gas law. We either have to use the Clausius-Clapeyron equation or we have to use the shortcut equation. And the students do a calculation to calculate then the pressure in the cylinders. So that's the module. View the video, fill out the safety analysis sheet, then do a bow tie diagram and do a calculation. Let's look at one more. I'll just cut this short. So let's go to the material and energy balances course. And this is CAPECO. It occurred in Puerto Rico. So
October 23rd, 2009. A massive explosion rocked the Caribbean Petroleum Terminal facility near San Juan, Puerto Rico. Gasoline overflowed and sprayed out from a large above-ground storage tank, forming a huge vapor cloud which ignited. The explosion damaged nearby homes and businesses. Petroleum leaked into the surrounding soil, waterways, and wetlands. Fires burned for more than 2 days, destroying 17 of the facility's 48 storage tanks.
Well, there's more to the video, but I only showed a small cut. Again, what was the activity? What was the hazard? Incident of CAPECO's, they had an unreliable floating tape measurement to tell how much gasoline was in the system. The gasoline overflowed. And again, you come down and you do a bow tie diagram. Potential problem. Mechanical failure of the float, excuse me, in the system. A route that measured the amount of gasoline in the system. Could have been a routine inspection, replacement of the measurement system, automatic overfill collection. So these are all preventative actions. Then the hazard and the overflowing of stakes was the initiating event. They could have then, a mitigating action would have been an alarm system and secondary containment. So again, let's get in the mindset of thinking prevent, occurred, mitigate. And again, they do a calculation and say how much gasoline vapor was on the ground at the tank, and they find out the number of moles of kilomoles of octane, enormous amount. Another one here is this is in heat and mass transfer.
June 13th, 2013. The Williams-Geismar-Olefins plant in Geismar, Louisiana. A heat exchanger violently ruptured, causing an explosion and fire that killed 2 workers. The Chemical Safety Board launched an investigation and issued a case study. In it, the agency describes a number of process safety management program deficiencies at Williams, which set the stage for the incident. In particular, the CSB found that the heat exchanger that failed was completely isolated from its pressure relief valve. When pressure inside the heat exchanger dangerously increased, there was nothing to stop a catastrophic rupture.
Okay. again, you do your bow tie diagram, accidental heating the liquid, the initiating event, and preventative actions. And then you do your calculation here. And one of the things, could have been, what is the thickness of insulation on the heat exchanger and so on. You do a calculation. And the final one I want to talk about is the chemical reaction engineering, and this is the T2 laboratories. And so let's go to here.
On December 19th, 2007, a powerful explosion and fire occurred at T2 Laboratories, a small chemical producer in Jacksonville, Florida. The blast killed and injured workers, destroyed T2 Laboratories, and extensively damaged 4 nearby businesses. Windows blew into offices, striking workers with flying glass.
Okay, there's more to that video. So in this one, those of you that have my book, this is in chapter 13. And this now is a living example problem. What I'd like you to do is go to my website and then go to living example 13. And then you can vary all these variables that occurred. This is the temperature that occurred as a function of time, the concentration, the pressure. And so you can then essentially, with this living example problem, you could say, what conditions would I have that would have prevented this explosion? And you use the Wolfram sliders. So let me just stop and say something about Wolfram and Python. This is the future of chemical engineering, and using Wolfram and Python, and using the sliders. So now we have these sliders on there. You go to this living example problem, and you can vary all these. So I don't ask a question anymore, is what is the conversion to achieve, what is the volume to achieve 50% conversion? Those type of questions are passé, they're old. What you do is you give the students the simulation, which is on the website, and you said, play with the sliders, vary the parameters, and then tell me what you find. Give me some conclusions, so that they vary all the parameters and learn about the reaction and the reactor in which it occurs. And then you write a set of conclusions. So you go away with a different understanding of how the reactor works, how the reactions behave. So I would encourage you all to go to my website, go to a chapter, particular chapter 13, go to this chapter or chapter 12, and vary the parameters using the Wolfram and the Python sliders. Now, Wolfram is free, so all you have to do is take 60 seconds to download it on your laptop. The same thing is with Python. So there's no excuse for not being able to use these. Now, I also have on my website, I also have the programs in MATLAB and also in Polymath. In Polymath, you just copy it and click and then load it into Polymath, and you can do the same thing. The problem with Polymath is you have to vary one variable at a time. With Wolfram and Python, they're just fantastic, and you really need to get in and be using Wolfram and Python in your studies. So please promise me at least go to the website in chapters 12 or 13. Okay, so here's one we got from industry. And so here's a storage container, this is from BASF, and they think there's corrosion inside, and they don't know for certain. And they would have to find, really, if there is corrosion, they'd have to shut down the plant. And this would be fairly costly, about $5 million. So let's apply R.W. Paul's 6 types of critical thinking questions to this situation. Now, when I teach, I always teach critical thinking. And what is critical thinking? Well, that can best be described by asking critical thinking type questions. And Socratic questioning is at the heart of critical thinking. There's 6 types of critical thinking questions. Questions about the question, questions for clarification, questions that probe assumptions, questions that probe reasons and evidence, questions about viewpoints and perspective, and questions that probe implications. Now, when you leave the university, you're going to go out in industry, and you're going to be in team meetings where you have maybe 5 or 6 people in a meeting discussing a project, a piece of equipment, or whatever. If you want to become really known as a resource to your company, when you have those meetings, think about a question you can ask, but make it a critical thinking question, not what's the weather outside today? Can we go outside and work? No, think about a a critical thinking question about the project at hand. So let's look at the first one. Questions about the question. The main purpose is, what is the main question you want to answer? What is the point of this question? Now, for the example we're considering, now we have this tank. We want to stop production. We want to take go inside the tank and look at the siding. Not what's the weather outside today? Can we? So here we go. Critical thinking question. So for this example, why do you think I questioned you about the corrosion under the insulation, considering the storage tank is only 10 years old? So that's an example of a critical thinking question about the question. Questions for clarification. What do you mean by that? For this example, are there industry-identified case histories about corrosion occurring under insulation? Remember, $5 million to stop the production and look inside this tank and see if there is corrosion. Questions to probe assumptions. What can we assume instead? How do you assume stripping the insulation is the only method to check for corrosion? You see these type of critical thinking questions we need to develop so we can start challenging things? Questions to probe reasons and evidence. What would be an example? Why has this happened? What evidence do you have that corrosion may have occurred in this tank in the last 10 years? Questions to probe viewpoints and perspectives. What is a counter-argument? What are the strengths and weaknesses of your viewpoint? So here will be, what are counter-arguments for taking all the insulation off and inspecting the tank? Well, one would be the fact is the cost. And questions to probe implications and consequences. What are the consequences if that assumption turns out to be false? What are the consequences of ethylene oxide leaking into the atmosphere on people, equipment, and the environment? Okay, so those are R.W. Paul's 6 types of critical thinking questions applied to this example where we have a tank that we think the corrosion is occurring under the insulation. Okay, let's look now at laboratories. Now, we all have laboratory safety. So these are very short videos we have. You would like it. I'm just going to look at one of these, but these are fun. These were made by electrical engineering students at the University of Michigan. As you know now, electrical engineers are doing a lot of chemical engineering work by making computer chips. If you looked at chapter 10, I describe how to make a computer chip on that. So when you have time, this one is fun right here, Food in the Lab.
These stupid goggles, I can't see a thing out of them. Much better. Huh?
So there's more of those that you can look at your own time. Now, I also put up there references from the chemical and AICHE, where they come out with the safety beacon every month. And now there's little questions about the safety beacon for you to answer, and then you can see the answers in red. And also the spotlight on safety in every chemical engineering progress every month. And you read the article, one page, and then you ask some questions, explain, and so on. So anyway, that's what's on the website. So the department put quite a bit of money into this, and they wanted to see how it went. So they evaluated. We had about 120 students in the thermodynamics course, and they said, how do the students like it? Here's the bar graph that virtually 80% of the students found extremely useful or moderately useful, and 90% useful, and very few did it. At the end of the students were asked to find questions, and they responded. It was insightful to learn and see the consequences when safety factors were not properly considered. It's a helpful experience and helped me to begin my study of safety in the context of chemical engineering. The safety module was interesting. I thought it was interesting. So anyway, in a nutshell, it got very positive reviews on the class testing that we had at the University of Michigan of 120 students. And the students continue to cooperate on that. And this then is just the people. We've had industrial members look and guide us in this, from Dow, Bechtel, Reliance, and so on. So the conclusions are the students viewed a number of case history and videos and analyzed them. The reoccurring safety algorithms, the boat diagram, and get across what we hope. They instill a mindset about safety, and that's what their purpose was. Every student has safety training rather than a small fraction of the class. Why? Is because there's a safety module in every course. The bow tie diagram is repeated in every course. And so they all get safety training. The students see disastrous consequences when safety conditions are violated and an accident occurred. These modules have received positive response from the classes. They were class tested, and now virtually all the modules have been class tested at the University of Michigan. So it's time to end, and if you don't stop on time, bad things can happen. So thank you, and I'll be happy to answer any questions. Hello?
Thanks a lot, Professor Fogler. Yes, I'm here. I don't know. Okay, great. Okay. Thanks a lot for your wonderful talk. And I will ask people now to write here when they want to make the questions. Then I'll call. And then please open the microphones and ask something.
Veronica, can you hear me?
Sure.
Hola, Bella. The problem is that I can't find the hand, so I should like to make a question.
You can talk and ask him a question.
Can I? Okay, thank you very much.
Sure.
Okay, Professor Fogler, my name is Professor Falabella from the School of Chemistry, Thank you very much indeed for this marvelous lecture. It is more than a pleasure. It is a privilege and an honor to have you here with us. I must confess that our students were pretty much excited about your lecture, because your book is a kind of Bible for all the students. But I should like to mention something that happened to us, some years ago in our laboratory in Petrobras, I was working at Petrobras, at that time, and something very peculiar happened in our laboratory, which was the fact that we were working with a liquid polymer, or rather a monomer, and then the reactor was loaded with this liquid monomer. But the reactor, the technician made a mistake, and the reactor was much too full with such a monomer. So when we closed the reactor, there was no room for expansion. And as the temperature raised, there was liquid expansion. And we all know that gas expansion is something that can be controlled. Nevertheless, liquid expansion it's almost impossible to be controlled. So the reactor exploded in one of our laboratories, just across the street, you know. And, well, this was a huge accident. And thanks God, there was no one in the laboratory when the accident occurred. Nevertheless, there was, a technician outside the laboratory who was about to enter the laboratory, and then he was pretty much harmed and burnt, So I should like to hear your opinion about something that you have briefly mentioned, which is liquid expansion in laboratories and in reactors, Thank you for your attention.
Well, the only thing I can say is, I don't know if Petrobras, on that reactor, they should have filled out a bow tie diagram on that reactor. What are the other things that could occur? In this case, they call those bleeds, boiling liquid, exploding vapor. So they should have filled out a bow tie diagram saying what could occur, what could be an initiating event, what could the operator do that it could have caused it, and then how could they have mitigated it. Only making people aware, every time you have a chemical reaction, what are the chances of runaway? What are the chances of a bleed? And so on. So that's my only advice. You're going to have many, many chemical reactions occurring throughout the chemical plant. I know it takes time, but the thing you should be doing is looking at every chemical reaction and have a little sheet, what to do if something goes wrong.
Okay, thank you very much indeed for your answer. And again, thank you for being with us today. As I have said, I have mentioned just a couple of minutes ago, it's more than a pleasure. It is a privilege to have you here, Thank you.
Thank you, Falabella. Please, who else wants to make a question? Just open the microphone and make a question for Professor Fogler.
I'd like to make a question, Veronica. Márcio?
Go ahead.
Professor Fogler, my name is Márcio. I'd like to thank you for your nice lecture. I think it's a very nice idea to integrate safety in the course of Chem-Eng. We at university, we tend to see if you have a gap in the course, you just create a course. If you have a gap in the formation, we just create, like we had a gap in safety, we create a course in safety. My question is, it's very nice to integrate safety in Chem-Eng. And course integration has been a question for different areas of chemical engineering. Do you see any opportunity to integrate another area or another course in the chemical engineering course? Well, I don't know if I'm very clear.
Yeah, I would just say two things. First of all, this is a mild deterrent for the professor teaching the course. A lot of times professors say, oh, I don't have time to integrate that. Well, these are like one homework problem. So that excuse for not using these in every core course just doesn't hold any water. In regard, what would be something else? It would be sustainability and having a module on sustainability in every course. If you want to learn about sustainability, go to Sorocaba. Boy, I'll tell you, their university, they measure everything, the watering the lawn, everything. It's just tremendous there. So I would say that would be something that I would say also could be there in addition to safety.
Thank you. I think it's a challenge for us to integrate different areas in the course instead of creating new things, a new course.
Right, and it's so easy. Just make a homework problem for the students, and keep it, confine it, keep it so that they can get it done, and the professors won't have to change their whole course. They just give a homework problem that makes the point. And if they see it over and over again about sustainability, about safety, then they're going to get a mindset about that.
That's great. We think we should learn about this, and here in Rio de Janeiro, I think we should you should integrate more this safety and now sustainability, I think, and think about more things that we can integrate in our course. Course integration has been a challenge in ChemEng. I'm very happy to see this website and this initiative. Congratulations.
Yeah, it's a minor infringement. One homework problem can do a lot. So you're asking, students to spend maybe 1.5, 2.5 hours maximum on each of these modules. That's nothing. It has big impact.
Thank you, Márcio. Who else? I wrote here to the students, if they don't want to talk in English, they can write the questions here in the chat, and then we can translate. No problem, because they are kind of shy.
Excuse me.
Go ahead, please. Go ahead.
Yes, I'm Jonas, and I am from Mozambique, and I'm chemical engineer.
Is that a Jaguar, Jonas?
In Mozambique in Africa, near South Africa.
Is that your car? Is that a Jaguar?
No, Jonas.
Jonas, that's what I mean. I see a picture of you by a Jaguar.
The car.
No, it's not my car. It's one of pictures that I did in China when I was there. Yes, but I am talking that I'm in Mozambique, here in Africa, near South Africa and Madagascar Island. First of all, it's a pleasure to stay and hear Professor Fogler talking about safety. My question is it possible to make some lessons from chemical engineers here? If it is possible, how we can make it, because we are looking at safety in Mozambique is very important thing, because we are getting more industries, and about safety we don't have like Master told, we don't have in course some lessons that are directly linked with safety. Is it possible to have some weeks or some days talking like small course for us here in Africa, especially for Mozambique? Thank you.
So your question is to have a course in Africa? Is that what you're asking?
Yes, I'm asking to have small courses from here in Mozambique.
I'll tell you a little story. It happened about 20 years ago, and more than that, 1996, so it's 23 years ago. I got an email from a professor asking me how to solve one of my homework problems. And it had he was from ZA. And I said, I don't recognize ZA. Where are you from? And he said, South Africa. I said, never been there. He said, you want to come? I said, yes. The next thing I knew, I had 2 business class tickets to South Africa, which I toured South Africa and gave lectures and met with students and industry. So I have been there, and I have given short courses and so on. And it's a lovely place. So yes, I've done that. But now we don't know how we're going to get out of this. I mean, we're looking at I've been out, not been out of my house for now over 4 months, just to go to the grocery store and so on. And this is going to be a long time. So you really can't say. I'm not thinking of what you have to be looking at what's going to happen after January 1st, and you really can't be looking before that. And I think Brazil, and it's the same problem that the U.S. is, that the cases are rising, and the people everywhere in these things, like in the U.S. and in Brazil and so on, just have to be responsible. Wear their masks. Don't get in groups. Social distance, and be rigorous about it. So we won't see anything until we have a vaccine. I don't think we'll be back to normal till we have a vaccine. Because even if they lift restrictions, I know people are reluctant to go to the restaurants, to go out, and so on. You can see that in New York. We lifted it. People still don't want to go out. Thank you.
Okay, thank you, Professor. Yes.
Thank you, Jonas. Great that you are in Mozambique and having attended this seminar. Very good. Professor Medronho has a question.
Oh, hello. My name is Ricardo Medronho. I work at Escola de Química. I am a colleague from the same department as Veronica. I would like to say that it was a great pleasure to watch your presentation. It was very good, and I liked it very much the idea of spreading safety issues through the different matters of the course. I think it's a very good idea. And I am a lecturer of particulate systems. So I think that, for instance, I could include powder explosion as a subject of my course. Do you have any other idea that I could use as an example of operating cyclones, hydrocyclones, filtration, centrifuge, or so on? Apart from powder explosion, would you give me an idea of what could I also include in my course?
Well, ad infinitum. There's a book written that just came out by the people at Exponent on dust explosions, and they gave a short course which I attended about a year ago. Now, in the new edition of my book, which will come out in August, I talk about dust explosion, but those are difficult to do. And so in chapter 14, where we have mass transfer limited, those explosions are usually mass transfer limited, how fast oxygen gets to the surface of a burning particle. But then you have multiple burning particles, and how do you treat those? So dust explosions are extremely important. And if you go to my website, you'll find in there an explosion, a dust explosion, where it blows up. But there's lots more things than that. What I'm looking for, it'd be nice if I had another Professor Flavio de Moraes to translate the next edition of my book into Portuguese, so that the students could benefit by that. Flavio did great. I wonder, is Flavio on this call or not? Do you know, Veronica?
Veronica?
Yes. Flavio should be here. I don't know why, because I told him last week he attended Medronho's webinar, and he said, okay, I don't know what happened to him. But about your new edition, indeed, I and Professor Frederico Tavares, we translated the last one, and the other one, I think the publisher here in Brazil took so long, and then you have a new edition, and they stopped the other one that we had translated again. And then the next one, I don't know, it's in August. There is some agreement between your publisher and here the Brazilian publisher. But Flavio, I don't know.
Well, I would encourage you to do this one. This one is, again, it's a mini paradigm shift because of all the Wolfram and Python problems I have. There's 80 simulations in this new edition, which you can go to and run. And I would love to have somebody in Brazil translate this edition. I'm encouraging it. I'm not holding anybody back. And I realize it's fairly rapid after the other one, but I turn 81 in October, so I don't know how many more editions are going to have. I don't think they're going to be any more, but I'd love to work with somebody or have somebody in Brazil translate the 6th edition.
For sure, I'm completely
There's more
sure.
jokes. There's more jokes in this edition.
LTCU is going to translate because it's like a bestseller here in Brazil, your book. Don't worry, LTCU will do it. But because this time you were so fast that they could not even sell the last edition. You have another one. But I know that you have so many examples, and it's very good. Very good. Many opportunities for the students and for the faculty members as well. I don't know if somebody else who wants to make a question.
Daniele Dalto.
Oh, sorry. Yeah, thank you, Medronho. Daniele, please. Go ahead.
Okay, thank you. First of all, thank you so much for this opportunity to listen to you today, Mr. Fogler. I studied using your book. It's a great pleasure. And I really like the approach using your website. And I have a question about another thing is, do you have some studies or articles show the importance of NFPA diamonds on laboratory glassware? Could you prevent laboratory accidents?
On my website, it says laboratory safety. There's 6 videos there you might want to use. 4 are funny videos. Now, I asked somebody, because they were comedy, like the guy that got acid in his face. And I asked one of my industrial people, should these be funny about safety? Because, that doesn't seem we should make fun about it. And he said, yes, because they'll remember it. So we have 4 humorous videos on there, and then about 4 serious videos. And I would encourage you to use those. We're also trying to get questions about laboratory safety that the students can do interactive. And there'll be like iClicker questions. You'll be given 4 possible answers, and then you'll select one. So yes, go to the website about laboratory safety. But I don't know, that's something would be worthwhile doing. And I've told anybody, look, if you at your university wanted to make one of those short videos, like you saw with the guy with the acid and the mouse, I would be happy to consider it for putting it up on the site, and then you have your university and your students. And the same thing goes for the YouTube videos. Have you looked at the YouTube videos on my reaction engineering website, like chemical engineering gone wrong, learn a new dance? Have you looked at those?
Not yet.
Okay, you want to look at those, and the same thing holds there. If you go to my website and click on YouTube videos, there's the YouTube videos made by the University of Alabama, and they were the first. And they have how to learn a new dance, like to the tune of YMCA, CSTR, and also chemical engineering gone wrong. So if your class or your university wanted to make a video for the reaction engineering, I'd happily consider putting it up there with the others and giving you credit, just saying where it's from. University of, what university are you with?
Federal University of Rio de Janeiro.
Rio de Janeiro.
Yeah.
Okay. So yeah, and listing that. So anyway, send me something either on safety or a 2-minute snippet on safety or a longer 6-minute YouTube video on chemical reaction engineering of your choice. But go to my website and click on the YouTube videos. They're pretty fun.
Okay, thank you so much.
Thank you, Daniele. I forgot to tell you something before giving a word to somebody else. Professor Fogler, you said that you are 81 and gosh, you were still young. Professor Bird is 96 years old and he is writing right now the third edition of his famous book, Transport Phenomena. Then don't worry, you are still very young. Some more new editions will come. Now, Professor Falabella raised his hand. I don't know if he wants to say something.
Yes, I do.
Okay, go ahead.
So, Professor Fogler, it's Professor Falabella again. So, allow me to make another question. It's a rather inconvenient subject, may I say so. It's about what is happening in the world regarding the coronavirus in Brazil, both in Brazil and USA. Okay, somehow I got the impression that wrong actions are being carried out in the universities and in many places, you know. Could you talk about what is being carried out in your university regarding safety procedures about coronavirus?
Yeah, our university is shut down. I got special permission yesterday to go into my office. I wanted to get a book or so, but we're slowly reopening the research labs. None of the staff is back. My assistant can't go back. Accountants are working. I've been working remotely since the second week in March, as have been most of my colleagues. Just now, we're starting to get the graduate students back to their labs that have to do wet chemistry. But we've greatly reduced the number that can be in there. So they're having 2 shifts, like 6 to 2 and then 2 to 8 or something like that, 2 to 10. Number of people that can be in the lab. Okay, when I went in the front door yesterday, here's what happened. First thing I had to do was I had to have permission to come in. And to do that, you have to take a test, multiple choice, and pass it. And then they'll put you on the list. So then I just click my university ID card to the outside, and the door will open. The next thing, I come in and they ask me a whole series of questions. They take my temperature, and then they let me in the building. And so that's what we're doing. And we have somebody in charge at the college level, at the department level, and we're greatly restricting the number of people that can be in the lab or in the building at a given time. It's about maybe a third of what's there. And this just started this last week, and we're going to do it by slowly. So everybody that enters the university, and the same thing if you go to the doctor, go to the hospital now. I have an appointment today for a blister. You go in, you answer the question, they take your temperature, and then they let you in the building. People are not social distancing or wearing their mask like I would like to see them. And I want to encourage everybody to do that, to slow the spread of this. There's also an interesting problem. If you go to chapter 7 in my book, there's a problem you can extend to the coronavirus by writing equations. You have a healthy person becomes ill. Well, it's H go to I with a rate constant. Then you have H, another healthy person contacts that ill person to give 2I. The ill person can die, or the ill person can recover. So you can go write those equations, and you can make some model predictions about the concentration of infected people as a function of time. And that also is a problem in the new edition of my book, which we modeled China.
Thank you.
So those are the precautions we're taking at the university. Nobody can go in the building without being checked.
Okay, delighted to hear that you have a model, a mathematical model for this problem we are facing right now. You know, as I have mentioned, I think well, we have a program regarding the return to the classes and to the laboratories. You know, but well, that's something that has to be looked into because well, this is a major problem in our society. You know.
Yes, it is. So anyway, I can tell you what's happening in the fall. They haven't decided what's going to happen. But my grandson also is just finished his freshman year at the University of Colorado. And his classes were called off in March as well. And they were all done remotely. So in the fall, for classes, large classes, larger than 50, they're all going to be done remotely. And if you have 50, that you have classrooms where you can get 50 people in 150 to 200 room classrooms so they can socially distance properly. But for the large classes, they're going to have all remote instruction. For the smaller classes, they're trying to work that out and see what they would do. The problem goes beyond that. What about the dorm rooms? Now, you don't have that quite so much in St. Paul and so on, because people work from home and then go in, and that's another issue. But their people are really trying to address it. So I think what's going to happen in the fall, large classes will be taught remotely, lectures and tape and everything. With the smaller classes, they're going to try to get, a classroom that holds 150. They might have 30 or 40 people come into that classroom and socially distance properly. But anyway. Looks like we're losing participants here. We're down to below 100 now.
Yeah. Well, in Brazil, we have already started, as far as graduate courses are concerned, we have already started some sort of remote classes, which I must confess are some sort of pain in the neck, because it's difficult to work in a remote way. We are not accustomed to that, But we are trying to do our best. And as far as undergraduate classes are concerned, we do not have a final decision yet.
Yeah. Well, you also ought to try, in reaction engineering, it's pretty easy because you have all these simulations that the students can do. You also have iClicker questions up on the website that the students can test how they're studying. There's lots of resources there that are one-on-one interactions for chemical reaction engineering. And I encourage everybody to really start taking Python and Wolfram seriously. That's where we're going in the future, with or without the pandemic.
Thank you. Great suggestion. Thank you very much indeed.
Thank you, Falabella. Now we have a question of Isabella.
So thank you, Mr. Fogler, for the presentation. I'm a chemical engineering student, and I work as a process and plant safety intern at a company. And sometimes I miss some kind of information from the university about, I think we should have a general view about safety, like Marcio said, at the university.
I'm sorry. We've lost you, Isabella.
Okay, I'm sorry, I was muted. So thank you for the presentation. I'm a chemical engineering student, and I work as a process and plant safety intern at a company. And sometimes I miss some kind of information about, for example, a general review about process and process safety, for example. I work at some HAZOP studies, and I think it should be nice to have at the university some kind of knowledge about this kind of safety analysis, and sometimes about some equipment, some information about flame arrest or pressure safety valves. Sometimes I get a kind of lost in the analysis, and I think that the university could help us with this. Do you think this is a point, or do you believe that we should only know this information when entering a company?
Well, of course, the more knowledge, the better. The real question is resources, isn't it, Isabella? Where are you going to get the resources to do this? Now, number one, if you go to my basic website, you'll see on there a link to Dr. Montgomery's Encyclopedia of Equipment, or you can just search her, Dr. Susan Montgomery, and she has an encyclopedia of various pieces of equipment. And you might find flame arresters on there you can learn about. So that's the first place I would look. That might be up there. It's called Encyclopedia of Equipment, and it's Dr. Susan Montgomery. But I think the link is there from my website. The second thing, sure, it would be nice. The question is, who's going to do it, and who's going to make the resources available? And that's the real question. It's nice, but we've got to find a pathway to get there. And that's the real hurdle. And again, I don't think we're going to be doing much till after a vaccine is done. I mean, I feel restricted. I can't really go out and do things, and I think everybody else does too.
Yes. Okay, thank you.
Thank you, Isabella. Lucas.
Professor Fogler, first of all, I'd like to thank you so much for this lecture. It was really an honor and a pleasure to be able to watch how we can integrate safety with chemical engineering. But my question is a little bit more personal, and it's about your books on how you decided originally to start writing your books and to share your teaching knowledge with us as chemical engineering students.
Oh, that's my favorite question, Lucas. When I came to the university back in 1965, I was assigned to teach reaction engineering, and we were using Levenspiel's book, which is a good book. But during the course, I found the students were memorizing all equations. If you had a first order reaction, it was gas phase, it was in a CSTR, this is the equation you would use. If it was a plug flow with liquid phase, second order, this is the equation. So they would come into class with a whole list of equations for every possible combination of reactions and reactors. And this, I said, this isn't the way to learn reaction engineering. Don't memorize, but give a structure to it. It's logic. And that's why my book took off. I start off and say, what reactor are you going to use? And then go on from there. What's the reaction rate law? What is the stoichiometry? And then you combine all those and you come up with the equation for your reactor. You don't memorize things, you just use logic. Reactor, rate law, stoichiometry, combine. And in the combine step, if you have heat effects, the computer program combines it for you, so you don't have to worry. So that's how I got in. I saw the frustrations the students had was memorizing equation after equation after equation.
Thanks so much, Professor.
We're down to 90.
I just want to make you a silly question, but I'm so curious to know, why did you choose this picture of the camel? It's because there is a face of a question mark.
Yes, exactly. He's just like he asks questions. And that's funny. On my trip to Israel, I got that picture out in the desert. I didn't take it, I bought it.
Okay, is there any more question? Gabrielle.
Marina is waiting. Marina? Curry? No.
Gabrielle wrote that she wants to make a question. Go ahead, Gabrielle. Is there anybody else, Professor?
No, nobody.
Okay.
I'm waiting now.
Okay. Go ahead, Gabrielle.
Hello, good morning, Professor Fogler. It's an honor to be here. Well, I use your books to study. I have one of your books here in the quarantine I am using to study chemical engineering of chemical reactions. But my question safety in industry. Well, here in Brazil, an incident that became known all over the country a few months ago. Well, summing it up, people got intoxicated by diethylene glycol in beverage produced by a beer company. Well, the police later discovered that there was a hole at the tank where the cooling process happened in this industry. And this way, the diethylene glycol mixed it up with the beer. This way, people intoxicated. Well, what do you think could be some preventing or mitigating actions that the company could have prepared in a bow tie diagram for this case?
Well, again, what would be the resources? Would they have a testing on, if I assume you're making the beer in a big vat and then bottling it, right? Is that correct? You
Yes.
mix it up in a big vat, and then you bottle it, and the contamination occurred when the beer was in the vat, right?
Yes, that's exactly what happened.
Yeah, so the only mitigating things would be a testing. If they had a system in place that they would test the tank every so often for certain chemicals. I mean, this would be fairly easy to do once they brainstorm and say what particular chemical could get into this tank, and they say, well, what could break to get in there, and then just withdrawing a sample and having a very specific test for it. They could test it every so often, or they could have even online monitoring of the tank looking for a specific chemical. So that would be one mitigating circumstance. The other mitigating circumstance is throw away all the beer off the shelves. And this happens a lot of time in the U.S. that they find something that's contaminated. They go after all the stores that have received that contamination, and they ask them to pull whatever it was from the shelves and throw it away.
Okay.
The problem, Professor, is that nobody could figure out there was a problem only when people start dying. And then lots of people at the same period of time, and then they decided to investigate it. And then they discovered that finally, after some months, they discovered that there was a leakage in this big vat. They discovered some weeks ago. It was really horrible.
Yeah, something like that. Yeah, they can only plan on the next one of using this to plan for other things that could occur. If they have another, if it were to occur again, of putting them on it. Yeah, you're right. But something had to happen, and they had to trace it back. I don't know if they would have found that. I mean, that was. I'm not sure any preventative. Well, you never know. You can never. Hindsight is 20/20.
Yeah, Professor Ajimiro made a comment. I don't know if he wants to say something. Ajimiro?
Oh, just to add a comment about that. No question about it.
Okay. Marina, I don't know. I didn't see if here. Is there any Marina here that who wants to make any question? Carolina, please go ahead.
Hello, good morning. Thank you for your lecture, Professor Fogler. I find it very nice that you have this interest in teaching safety and critical thinking in the chemical engineering courses. As Professor Falabella, I would also like to make a question related to the coronavirus crisis. Now that people are paying attention to safety of humans against diseases, do you think that this is an opening path to people also paying attention to safety as a whole, including chemical processes and industries, for example? Or even what are the changes you think are going to happen in the world after the coronavirus crisis?
Well, the problem is here in the U.S., if you see, and I think the same problem in Brazil, is people still aren't taking this seriously. In New York, Governor Cuomo He did a fantastic job. I mean, they rose up the cases. He was on the TV every day. He was saying, look, folks, it's up to you. Wear the mask, social distance, don't go out in crowds. And now New York is down in very few. It's a model system. And shortly after that, New Jersey came on, and they're down. And Connecticut, all the states standing around New York. So it shows that if people behave and follow the rules, masks, no crowds, and so on, that we can beat the virus. But what's happening now in California, Arizona, and Florida is that people are going out and not paying attention to these rules. And it's mostly the younger people now that want to go out and party. Say, oh, it's not going to affect me. Well, it will affect you, and most likely very few will die. The problem is you could infect an older adult, and that's the real problem. They're thinking what about me? I want to have fun. I want to do this. Hopefully our social norms will change, but this is going to go on. We're not going to be out of this till we have the vaccine. And I know Brazil now is just second only to the U.S. in the number of cases. And I'm not sure how serious people are taking it in Brazil, but I know some in the U.S., there are regions that aren't taking it seriously. In fact, I heard yesterday that 45 out of the 50 states, as a result of the weekend some time ago, have had an increase in the number of coronavirus cases. We just have to reinforce each other, say, keep doing what you're doing, following Governor Cuomo of New York, social distance, wear your mask, don't go out unless you have to. So I don't know if that answers your question. I can put my mask back on if that'll help.
Yes, thank you, Professor. Yeah, you're completely right. Here in Brazil, we also have this problem, as you said. Not everybody's following the rules. Not everybody is aware of the dangers of the virus. But what I really would like to know is if you think that maybe for the people who are getting the conscious about the problem, if we are able in the future to extend this awareness of safety to the chemical processes and to prevent accidents and also other pandemics.
Yeah, but that's exactly what I want to achieve by this website, where you have it in every course. So when a student leaves the university, they've had safety instilled on them. They know what a bow tie diagram is. What could you do to prevent it? What can you do to mitigate it? So I want them to have a safety mindset by having one of these modules in every single core course. See it over again, and they just leave there. Of course, I have to look at safety. I got a new piece of equipment. Now, what could go wrong with that piece of equipment? And so on. So the goal of the website is to develop a mindset about safety.
Great, thank you.
Thank you, Carolina. We have one more question of Deborah, and if somebody else wants to make a question, please write in the chat because it's kind of late, and Professor, we need to give him a break. Okay, Deborah, go ahead.
Hi, Professor Fogler. It's a pleasure to be here listening to you today. And my question is a little personal. I would like to know, why did you choose chemical engineer?
Oh, it's simple. I was good at math, and I like chemistry and math. What is chemical engineering? It's a combination of chemistry and math.
I think that everyone says that when we ask about that.
And chemical engineers are modelers now, to write equations, to put differential equations, algebraic equations to describe things.
Thank you so much.
Okay, great. Gabriel, the last question of the day.
Hello, Mr. Fogler. It's an honor to see your lecture. I'm very nervous, sorry, and sorry for my English. But my question is, how do you think the chemical engineering job market will react to this coronavirus crisis?
That's a $64,000 question. We have to be farther along. Apparently, the jobs market's coming back. I saw today they got the jobs report for June. And the unemployment rate now is 11%, down from, it was up 20%, then 13%, now it's 11%. That's still catastrophic. It's more than the recession. But, you know, we have to see, and we have to see what's going to be coming back. I mean, until we have this vaccine, nobody can say what's going to happen, I think. That's my opinion, but I'm just one lowly person.
Okay, thank you so much.
Okay, great.
Veronica, may you ask one last question related to...
Sure. I think Professor Fogler wants my...
The last one, I think. How do you think Cambridge will react to the artificial intelligence boom, Professor Fogler?
How do I think chemical engineering will react to
artificial intelligence boom?
Oh, artificial. Well, you know, I notice it when I write you letters now. I write emails. They've already incorporated artificial intelligence in my emails. I'll try to write a sentence, and then all of a sudden it'll come on the screen the last part of that sentence. Have you had that happen in your emails?
Oh yeah.
Yeah, so that's part of artificial intelligence.
Yes. I also think that for chemical engineering, the impact is not going to be so large, maybe for another professions. Thank you.
We'll have to wait and see. I'm not sure. I wouldn't comment on that, but anyway. Well, let me say it's been a pleasure talking to you all. We got 80 people that hung in till the end. I've always enjoyed visiting your country. I don't know, is there anybody here from Florianopolis University there? I gave a lecture there almost 20 years ago in that. I've visited Ugusu Falls twice, Rio, and at least 5-6 times, and up in the mountains where Professor Nunez. I'm sorry, I should have emailed Nunez to be on this. When the conference was in Brazil, is when I first met him, and that was in about 2009. And he's not only a professor, he and his wife are fantastic ballroom dancers. So he's a professor of chemical engineering, and he's a fantastic competitive ballroom dancer, if you get to know him, Professor Nunez. But anyway, that's the trivia there. I love the country of Brazil, love your feijoada. My wife does make a fantastic feijoada, but it takes her all day to do it. And so we don't get that very often, but we have the original the Brazilian residency. And Enrique, if you're still on, again, I thank you for that dinner. I wasn't going to be in Sorocaba on a Saturday to get feijoada, so he got one of the restaurants there to make it on a Wednesday for me. And that was really nice. But I love meeting with the students, and I wish you all the very best. And please stay safe, wear your mask, encourage others to social distance, and to wear their masks. So that's all I have. Enjoyed being with you all. So have a good rest of the year, and let's hope the vaccine comes soon.
Thanks a lot, Professor. Indeed, we had more than 100 people attending your seminar by YouTube, and you were there too. After, I'll send you the address. And we have here more than 100, indeed more than 230 people attending your seminar. It was a really great pleasure to have you here. And when I wrote to you an email, you answered me very fast. And let me open my camera. And I'm so grateful for this. And I really hope that we can be all safe very soon, and that people be careful and take care of everything. And Professor, anytime that you want to come to Brazil, please don't wait for our invitation. It's made since now. And
okay, thank you so much.
I don't know if everybody can turn the microphone on and have a clap.
Thank you. Thank you very much.
Thank you, Professor.
Bye-bye.
Bye, great talk.
Professor, good to see you again.
Thank you.
Thank you, Professor Fogler. Thank you so much.
On as well.
Talvez foto família, não sei se é possível.
Thank you, Veronica. Thank you, Professor Fogler. Bye-bye.
Thank you very much.
Bye.
Bye-bye.
Thank you.